Okay, so in today's lesson, you're going to have to revisit some of the stuff from first semester. Yes, that class ended technically, but it's a prerequisite for statistics too. So the very last thing we talked about was normal distribution, right? Z-scores, all that stuff. Before that, what did we talk about? Can you remember? I know it was weeks ago, but can you remember? Remember the P's and Q's, the binomial probability distribution, where we made that big long chart and would figure it all out. Remember that? Okay. And then before that, it was just a probability distribution where you had x and then p of x, and I always made you find the sum of the p of x's. It had to add up to 1, equal 1. Otherwise, it's not a probability distribution. Remember all that? Okay. So we're going to come back to that today. That's why I wanted to make sure you remember that chart we made, the x, p of x, then x times p of x. What was x times p of x? Do you remember the sum of it? The mean. Yes. Okay. Good. So you do remember. You just need something to help jog it, right? All right. So sampling distributions is section 1. The mean of a sample is not necessarily the same as the mean of the population. That makes sense, doesn't it? Let's say you take Patrick Henry Community College, right? And you find the average height on campus, and then you find just a sample of 20 people and you find the average height. It's not necessarily going to be the same, right? So then think about if you take a mean of a second sample from the same population, it's not necessarily going to be equal to the population mean either, and it's not necessarily going to be equal to the mean of your first sample, right? They could be totally different as well. Hopefully similar, but they don't have to be exactly the same, all right? So a sampling distribution of a sample statistic is the distribution of values for a sample statistic obtained from repeated samples, all of the same size and all drawn from the same population. So what you do is you have your population and you say, I'm going to take sample sizes of 20. So you collect 20, then you collect another 20, then another 20, then another 20, and you take that information and create a sampling distribution with those samples. Does that make sense? Okay. And then just recall, because this was way back in chapter 1, a random sample is a sample obtained in such a way that each possible sample of fixed size n has an equal probability of being selected. Completely random, right? Yeah, did you fill in all your blanks on this page? It's the first two. Well, you were listening to me instead of writing. I'm okay with that. Okay. So you're good with that slide? All right, that was section 1. Yay. Good job. I mean, basically, it's just, I think it makes sense, you know, that if you have a mean for a population and you take a sample, you might get something a little different for the mean. And then if you take another sample, you might get something a little different. So you can take all those sample means and then create a distribution with them. And that's it. That was section 1. Okay? All right, so what is section 2? It's the sampling distribution of sample means, which we call the SDSM. If all possible random samples, each of size n, are taken from any population with a mean of mu and a standard deviation sigma, then the sampling distribution of sample means will have a mean of mu sub x bar that's going to equal mu. Do you understand what that's saying? What's x bar? What's x bar? That's sample mean, right? Well, what did we just say? We can take many samples of the same size from the same population, right? So if you take a sample of 20, you can find its mean, and you would call it x bar, right? Then you would take another sample of size 20, and it would also have an x bar, then another one, and another one, and another one. So if you find the average, which is mu, mean, of the x bars, then it's going to equal the mean of the population. So that's mu sub x bar. It's saying mu sub x bar is equal to mu, which is the mean of the means of all your samples is going to equal the mean of the population. So right there, if you need to write some stuff down to help yourself remember that, the mean of the means, maybe, the mean of the sample means is going to equal the mean of the population, that's fine. Okay, if you have a standard deviation of sigma for your population, then your standard deviation for your samples distribution is going to be equal to sigma of x bar equals sigma over the square root of n. Now, the square root of n is your sample size, not the number of samples you take. So what I was saying, we have Patrick Henry, and then I said I could take a sample of size 20 and find the average height. Then I could take another sample of size 20. So n would be 20, not the number of samples I take. Does that make sense? Because I could take a sample size 20, do it again, and do it 10 times and have 10 different average heights. N is 20 because that's my sample size, not 10 because that's how many I took. So keep that in mind in your head, because when I was first doing this, I got all mixed up with, wait a second, which one's N? You know, because normally N is the number of samples you do, right? Number of samples you have, but in this case it's not, it's your sample size. Okay? So you have sigma sub x bar. This is the standard deviation of your samples. It's the standard deviation of your sample means. That's what sigma sub x bar means, okay? All right, so if the sampled population has a normal distribution, then the sampling distribution of x bar will also be normal for samples of all sizes. Can we put that in our own words? What is that saying? If the sampled population has a normal distribution, then the sampling distribution of x bar will also be normal for samples of all sizes. So what does that mean? That means if the heights of the Patrick Henry students, which are Patrick Henry students, right? If they're normal, then I could take heights, and instead of doing a sample of size 20 heights, I could do a sample of 5, and another sample of 5, and another sample of 5. And they're going to be normal because the parent population is normal. That's what that means, okay? So if your parent population is normal, automatically any samples you take from it, when you put the distribution together of all those means, those averages, it will be normal, okay? Your sample itself may not be, but your average, when you put it with all the other average from the samples, it will be. It'll be normal, okay? All right, so standard error of the mean is what sigma sub x bar is. That's called standard error of the mean. The standard deviation of the sampling distribution of sample means. And then we have what's called the central limit theorem. We love the central limit theorem. It's very useful. The central limit theorem is the sampling distribution of sample means will more closely resemble the normal distribution as the sample size increases. So like what I was just saying, if you don't know the distribution of the population, then the larger your sample, the more it's going to be normal. So if you take just a sample of size 5 and do it again, and you take those means and put them together, it might look approximately normal. But if you take a sample of size 20 again and find those means, it's going to be more close to normal than the one that was sample size 5. That's what the central limit theorem tells us, okay? So the moral of the story is it's normally better to have a larger sample because then you don't have to know as much information about the population. Okay? And didn't you learn that first semester when you did your own research for your projects? Typically, wasn't it better to have a larger sample because it was more accurate for the population? Yeah, because a lot of you said that in your presentations and things. All right, so what can we say about the central limit theorem? If the sample distribution is normal, then the sampling distribution of the sample means is normal, and the central limit theorem is not needed. So if the parent is normal, any samples you take and find the average and put them together, that distribution will be normal. Do you understand why I keep saying that? It's the sampling distribution of sample means. It's not that you're making a histogram for each sample and then another histogram and another. No, you take a sample, you find its mean. You take another sample, you find its mean. You take another sample, you find its mean. And you put all the means together to create a histogram. That's what we're saying. That histogram will be normal if the parent population is normal, automatically. So you don't need the central limit here. If it's not normal, then the CLT tells us that the sampling distribution will still be approximately normal under the right conditions, which are if the sampled population distribution is nearly normal or almost normal, then the X bar distribution will also be approximately normal, even if n is small, even as small as 15. But when the sampled population distribution lacks symmetry, meaning it's some weird distribution like J-shaped or something weird, right? Then n might have to be quite large, maybe 50 or bigger, before the normal distribution will provide a satisfactory approximation. Everybody got that stuff written down on that page? Okay. All right, continuing with the central limit theorem. By combining the preceding information, I almost said previous, preceding information, we can describe the sample distribution of X bar completely because the location of the center will be the mean of the means. So mu sub X bar is going to equal mu. The measure of the spread, which we call standard deviation, right? What's the variation in the data? The measure of the spread is the standard error of the mean, which is equal to the standard deviation of the population divided by the square root of the sample size. This slide's super helpful, y'all, because it sums up the CLT with these three statements, okay? So you really need to know it. All right, and it also tells us an indication of how it is distributed. The distribution of the sample means is normal when the parent population is normally distributed, and the distribution of the sample means becomes approximately normal regardless of the shape of the parent population when the sample size is large enough. So that's why we love the CLT, because even if the parent population is not normal, if we take large enough sample sizes, then our sample distribution of means will be, okay, will be approximately normal. Are you good? Need to take a breath? It's cold in here? Okay. I'm sorry. I know. The air cut on first block. I know. I can't control it. I'm sorry. All right. Thank you, though, for telling me what's going on. Consider all possible samples of size 2 that could be drawn from a population that contains the three numbers 2, 4, and 6. First block asked me a really good question, and I honestly couldn't answer it as well as I wanted to. You know what I mean? They said, how did you know that? Because they started saying, oh, 2 and 4, 2 and 6, 4 and 6. And they were like, done. But that's really not. So the way you have to think of this is with replacement. So you could have 2, 4, or 6, or you could have 2, 4, and 6, and make sure you leave room in between them like I am, and I'll show you why in just a minute, okay? All right, so then If you draw from that, it would be that you could have a 2 and a 2, a 2 and a 4, or a 2 and a 6, right? This one would be a sample of 4, 2, 4, 4, or 4, 6, and this one would be a sample of 6, 2, a sample of 6, 4, or a sample of 6, 6. Do you see that those are all samples that you could draw from that population of 2, 4, and 6? As long as you think of it as with replacement. Yeah. So then if this is a sample, this is a sample, this is a sample, all of those are samples. Can you find the mean of each of those samples? Could you find the mean? What would the mean be of these? 2 plus 2 divided by 2? 2. 4 plus 2 divided by 2? 3. 6 plus 2 divided by 2? 4. So the mean of this sample is 2. The mean of this sample is 3. Does that make sense? All right. So we can find the mean of each of these samples as well. So we'd have 3, 4, 5, 4, 5, 6. So you have all of your possible samples of size 2, and then you have all of your means for each of those samples, okay? All right, what's the population mean? If the population is 2, 4, and 6, then the mean is what? Don't you just add them all together and divide? So 2 plus 4 plus 6 divided by 3, which is 4. Now, do you remember what you had to do for population mean? If it was population, remember you had to make the chart, write all your x's, and do x minus mu, and then do x minus mu squared, blah, blah. Okay, if we don't want to have to do that, what we can do is talk about if it was a distribution of 2, 4, and 6, right? And we could do x times p of x to find our mean and then our standard deviation. So that's what we're going to do on this next slide. And what I want to point out, leave yourself room. You know, don't write super huge, okay? So if this is x, then this is p of x, then this is x times p of x. Do you remember what came next? It was x squared, good job. And then the last one was x squared times p of x.
Which one's x, y?
You're thinking about linear regression, x, y. But you are right that the last thing is summation. But we don't find all the sums, just some of them, right? So our x, what's our population? 2, 4, and 6. So if that's our population, then what's the probability of getting a 2 if it's 2, 4, and 6? If you have a 2, a 4, and a 6 on a ball in a bag, what's the probability you'll draw the 2? 1/3, yep. What's the probability you'd get the 4? 1/3, and same for the 6. Okay. So now we're going to do x times p of x. Actually, let me pump the brakes. Is this a probability distribution? Yes, because this column adds up to 1. Remember, I always had you check that, right? Because there was no point in continuing if it didn't. All right, so now we can do x times p of x. 2 times a third is 2/3. 4 times a third is 4/3, and 6 times a third is 6/3, which yes is 2, but it's actually easier to add together if you don't reduce it, right? Because it's got a common denominator. So 2 plus 4 is 6. 6 plus 6 is 12. So we get 12/3, which is 4. Why did I find the sum of this column? because that's the mean. So mu of the population is 4. And we got that right there from the sum of that column. Excuse me. All right. Now x squared, 2 squared is 4, 4 squared is 16, and 6 squared is 36. So now we do x squared times p of x. So 4 times a third is 4 thirds. 16 times a third is 16 thirds. And 36 thirds. And then, yes, I do need the sum of that column. So 4 plus 16 is 20, and 20 plus 36 is 56. So we get 56 thirds. All right, so now to find the standard deviation, we do the sum of this column, which is x squared times p of x, so 56 thirds, minus the mean squared, so minus 4 squared, and we square root the whole thing. Remember? Okay, so we get the square root of 56 thirds minus 16. So common denominator would be 3. So 56 thirds minus, what's 16 times 3? 48. Very good. I knew you were going to get it, so I was giving you just a second. Okay, and now we can subtract 46 minus 56. 56 minus 48. 8, right? So we get the square root of 8 thirds. And now you can type that in your calculator. Y'all had me last year. You know I work them as far as I can. But calculators are good to help with standard deviation. So we get about what? Right. You can write just 1.63. That's fine. Okay. I will look and see if I have some batteries for you. Okay. And while I'm doing that, y'all can fill in this chart. What did we talk about? What's the whole point that we've been talking about today? We found the population mean. Now we found, look at what we did. Found the population mean, right? Then I wrote all of my samples of size 2 that I could have, and then what did I do? I made all the means for each of them, right? So look at your sample means. These are all sample means. They're all X bars, right? You have a sample mean of 2, a sample mean of 3, sample means of 4, sample means of 5, and sample mean of 6. So making the same kind of chart, but we're using X bar instead. So what are my choices for X bar? Look at your sample means. What are they? The 2, 3, 4, 5, and 6. Okay, so what was the probability? May God bless you. You're welcome. What's the probability of having a mean, a sample mean of 2? One out of 5? It happened one time out of 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1/9. Do you see how to fill out this chart? So then what's going to be next? X bar times P of X bar. And then what's going to be next? X bar squared. And then the last column? Very good. X bar squared times P of X bar. Exactly. All right, I'm going to look for some batteries for him. All right, so did you have 1/9 and then 2/9? and 3/9, which yes, you could reduce, but you know, it's easy enough to add it up to make sure it equals 1 this way. 2/9 and then 1/9, and then yes, that's 1 plus 2 is 3, plus 3 is 6, 8, 9, 9 over 9 is 1. So yay, it works, right? Then when you multiplied, you got 2/9, 6/9, 12/9, 10/9, and 6/9, right? And then x bar squared, 2 squared is 4, 3 squared is 9, 4 squared 16, 5 squared 25, and 6 squared 36. So now we take this column and multiply it by the p of x bar column. So 4 times 1/9 is 4/9, 18/9. Then, why am I blanking? 16 times 3, 48/9. Sorry, needed a second. 50/9 and 36/9, right? So when you add all those together, did you get 156 over 9? Which that does reduce, you know, and you are welcome to reduce it if you want to. I didn't. First block did, which I think is awesome. So 52 over 3. So now we can do the same thing, but I did not finish that, did I? Which column should I have added that I didn't? The middle one, yeah. So 2 plus 6 is 8, plus 12 is 20, plus 10 is 30, plus 6 is 36. And 36 over 9 is 4. So we just found the mu of the x bars. So the mu of the x bar is 4. You just found that the mean of the means for those samples is the same as the population mean. That's what central limit theorem tells us. This is why, though. So I feel like you'll appreciate it more and probably remember it better because you have to do the work. And yes, you do have to do one of these on your homework, where you actually find the mean over here for the population, then you find it over here, you know, to verify that they are the same. So we are going to find the standard deviation, though, for the x bars, which is the sum of this column, so 52 over 3, minus the mean, so minus 4 squared, and then we square root it. So we would get, again, 52 over 3 minus 16, which we found over there was 48 over 3, right? So we get 52 over 3 minus 48 over 3, which is 4/3, right? And then you square root that, and you get 1.15. So that's the standard error of the mean, the standard deviation of your sample means, the standard error of the mean, okay? What's the formula? You know, if you didn't want to have to make this big chart and do all this work, what's the formula to find this standard error? I just gave it to you today. Sigma sub x bar is equal to sigma over square root of n. So we found sigma to be the square root of 8/3, right? And divide that by the square root of n. N, remember, is your sample size. So you were drawing samples of size. What were my sample sizes? 1, 2. That's a sample, right? So it's of size 2, 2, 2. So n, my sample size is 2. Go ahead and divide those. Square root this and divide it by the square root of 2. And what do you get? .15. Amazing. Isn't it amazing how statisticians, mathematicians have figured out these formulas that actually work? I mean, I think it's amazing, don't you? A lot of free time? Well, you know, and you don't have computers and phones and things to obsess over. You have time to figure out these life questions, like sample distribution of sample means. What's the standard deviation of it? Yeah. I think it's amazing. I'm serious. I think it's amazing. And people are still creating things. I'm not taking away from technology. It's amazing. But, you know, in the same aspect, if it consumes all time and you're not creating or learning.
Well, I mean, look at it this way. Math was used to create this technology.
Yeah, math was used to create the technology. You're exactly right. It's pretty awesome. All right, so a couple more things and we're done today, okay? If a population has a standard deviation of 25 units, what is the standard error of the mean if the samples are of size 16? What's the standard error of the mean? So what's that formula? Sigma, which is the standard deviation of the population divided by the square root of n, which is your sample sizes, right? So we get 25 divided by square root of 16, which would be 25 over 4, which is 6.25, right? Because it would go into it 6 times with a remainder of 1, so 6 1/4. Okay, if the samples are of size 36, then the standard error is 25 divided by the square root of 36, which is 25 over 6, which is about 4.167. Okay, and the last one, 25 divided by the square root of 100, which is 25 divided by 10, which is 2.5. What do you notice about the standard error as your sample size increases? It gets smaller. Yep. So it's more clustered about the mean, right? So is it important to have a larger sample size? If at all possible. Yep. Okay. Like your what? Your 1,200 songs. Yeah, you go, girl. That's awesome. Okay, last thing, just to show you, if the parent function, not function, I'm so used to AMA, did you hear that slip? Sorry. If the parent distribution is uniform, if you take samples of size 2, do you see that doesn't look very normal, does it? But then if you take samples of size 5, it's starting to look pretty normal. And then if you take samples of size 30, it looks pretty normal, doesn't it? Okay. If the parent distribution is U-shaped, that looks really weird, doesn't it? Okay, it's definitely not normal. So if you take samples of size 2, this is clearly not normal for my distribution of the means, right? If I take distribution of X bar for when the sample's 5, it's starting to get there. But again, see, when we take it of 30, it looks even more normal, right? All right, if the parent distribution, is J-shaped, clearly when we take a small sample, it's not normal, right? Again, have to get a bigger sample before it starts to be more normal. And then if the parent once I slipped up, now it's over for me. I just can't help it. Parent distribution, not parent functions. Distribution. Do you see it's normal? So look, when you take a sample of size 2, it's normal. Sample of size 5, it's normal. Sample of size 30, it's normal. It does not matter how big your samples are. When the parent function's normal, it's automatically going to be normal. Okay? Any questions? That's it. Okay?